Okay, so this is going to be our last video lecture associated with exponents. And this is also logarithmic equations. You can see they were fascinated by the last set of logarithmic equations, so they decided to stay with us. These equations are given to you where they actually have a log in them. So in all the other cases, you had exponents. The equations start off by giving you a log. So let's take an example. Let's say that we have we'll just put in here to separate it more logarithmic equations because they're so exciting. They really are. They're kind of cool. So I'm going to put a 1 here. Okay, different kinds of logarithmic equations. Okay. So before we start, actually I'm going to erase this one because there's something that is important to mention. Okay. The argument of a log cannot be negative. And it can't be 0. Other problems that we did in the last lecture, it was okay if our x wound up negative. It even would have been okay if our x were 0. That's because if we raise something to a power of 0, it's 1. If we raise something to a negative power, we can still calculate it. But for a log, we can't. Remember what the domain of a log is. The domain of a log is x must be greater than 0. Okay? So the argument of a log must be positive. That's because what the argument of a log is saying is if you take a base and you raise it to a power, can you get something negative? And the answer is no. There is no base that you could raise to any power that will give you a negative number as the answer. Okay, so the argument of a log has to be positive. There is no number that you can raise to a power and get a negative answer back. Logs, we're saying a to what power is a. Okay, if we had a log base a of b, we're saying a to what power is b, and we're saying b can never be negative. Okay, so this is something that we have to check for. Okay, we've talked about in radicals, we've talked about extraneous solutions and radical equations. I think we've talked about it in other equations as well, that sometimes we have extraneous solutions. Here we have to check for those extraneous solutions again. We have to make sure that when we plug x back in, we don't get a negative argument or an argument of 0. Okay, so let's just take a few different types of equations. So now we can put this one. And we're going to say log base 2 of 3x plus 4 is equal to log base 2 of 8x minus 2. Now this equation is kind of nice, okay? And the reason why it's nice is that the base is the same. So this is going back to that very last property of logs that we didn't use when we were condensing or expanding. Now we're using it. Okay, so this goes back to that property that says if the bases are the same, the arguments are the same. The arguments are the same, or we would say the arguments are equal. This is that last law, that last property of logarithms that says if, again, I'm just going back to check and make sure I'm using the same letters. That's why there's a pause. If log base b of x equals log base b of y, then x is equal to y. That is that very last property, okay? So here, the bases are the same. So the arguments are the same. So the next step is just to ignore the logs. We are not canceling the logs. We're ignoring them. There is a difference, okay? The difference is that if we say that we're canceling them, then we're saying it's possible to divide by log base 2. But you can't. It's like dividing by a plus sign. You can't divide by a plus sign. Over here, we can't divide by a minus sign. We have to divide by something. So log base 2 by itself means nothing. It's just, you know, the log of a tree. It's totally irrelevant. You have to take the log of something, which is why when I told you at the very beginning of logs, I said, when you do this, you have to say it as log base b of x, okay? That of is really important. That's our input. So we want to say that we're ignoring the logs. We're not canceling them. We're not crossing them out. We're saying, okay, the logs, the bases are the same, so therefore we can make this conclusion that the arguments are the same. Same thing with the exponents at the beginning of the last video. We said if the bases are the same, the exponents are the same. So here we can just set the arguments equal to each other. So 3x plus 4 is equal to 8x minus 2. And then we have this nice little neat linear equation that we can solve. So we're going to solve for x. We're going to subtract 3x from both sides, which means that we're going to add 2 to both sides. And we get 6 is equal to 5x. Divide both sides by 5. Which gives us x equals 5 over 6. Now we are not, sorry, x equals 6 over 5. So here we have to check for extraneous solutions. What we're checking for is that the arguments are positive. So it's always the arguments of the original equations. A lot of times it won't work if the x is negative, but that's just by coincidence. The x can be negative. So what we're looking for is that 3 times 6 over 5 plus 4 is greater than 0, and it is. Okay, then we're also looking for 8 times 6 over 5 minus 2 is greater than 0, and it is. Okay, both 6 over 5 is greater than 1, so we have an 8 times something greater than 1. So this is going to be a number larger than 8. Okay, 8 times something greater than 1 gives us a number larger than 8. And we know if we subtract 2, it's still going to be greater than 0. But you can always plug it into your calculator. Okay, so x equals 6 over 5 is not extraneous. because both our arguments are greater than 0. Okay, it's not extraneous. You don't have to write not extraneous. You can just box it. I'm writing not extraneous here, just for your benefit. Okay. Let's take another example. Let's say that we have log of x plus 6 is equal to 2 times the log of 7. So here's the thing, both of these have the same base, but we can't set them equal to each other if there's a coefficient, okay? So they have the same base, but we can't set them equal to each other until we get rid of the coefficient. How do we do that? We just go backwards. We take the 2 and we move it into an exponent. So what we get here is the log of x plus 6 is equal to the log of 7 squared. Now the bases are the same. If the bases are different, we can't do anything at all. Okay, there's nothing that we can do. Here the bases are the same, so we could say x plus 6 is equal to 7 squared, or x plus 6 is equal to 49. Subtract 6 from both sides. So this gives us x equals 43. And we're going to just double check. 43 plus 6 is greater than 0. So this is an answer. It's not extraneous. Okay, you have to check for those extraneous solutions. Okay. Those are straightforward enough. Let's take a look at some more. Okay. So in these, what we have is we have multiple logs on each side. Okay. So we're just going to do a whole bunch of problems. Let's say that we have log base 2 of 3 plus log base 2 of x equals log base 2 of 5 plus log base 2 of x minus 2. Okay. Now what's different is that we have multiple logs on each side, and when we have multiple logs on each side, we can't set anything equal to each other, okay? We can only set equal to each other when we have one log on each side. So we have to condense these, okay? We have to condense the logs on each side into one log. And the whole point of that is so that we could set them equal to each other in the end. Okay, again, if you have different bases, you're stuck. So we're adding logs, so we multiply. This is log base b of x plus log base b of y is the same thing as log base b of x times y. That's what we're using here. So we can do both sides at the same time. So this is log base 2 of 3 times x. And this is log base 2 of 5 times x minus 2. And you could skip this step if you want. I'm putting it in here just so that you see where it's coming from. So now you would have to distribute this 5. So we would have log base 2 of 3x. Notice it's always going in parentheses. Log base 2, and then we get 5x minus 10 when we distribute. Okay, so the addition, we condense it by making it one log, and we multiply. Okay, keep in mind it wouldn't make sense to do log base 2 of 5 plus x minus 2. That would be saying that having that extra log in there it serves no purpose. It does. Things have to change. When you condense it, the addition turns into multiplication. Okay, so then we have the same base, so therefore the arguments are the same. So 3x is equal to 5x minus 10. So we're going to subtract 5x from both sides. This is a linear equation. We're solving for x. So we have negative 2x is equal to negative 10. Divide both sides by negative 2. And we get that x equals 5. And we're not done. Okay, we have to check for the extraneous solutions. So, and here it might be obvious, but you still, again, you have to show me that you knew to check. So you have to show something, okay? So we don't have to plug it into this one because there is no x in this argument. So we're not plugging in a 5, but we do have to plug it into this one. So we're gonna say, okay, 5 is greater than 0. This is your check for extraneous solutions. If you don't put this, I don't know that you knew to check for this. And then we have to plug it into this argument too. So it has to be, every argument must be positive. 5 minus 2 is also greater than 0. So this is a solution. We want to plug x into every argument. Okay, because sometimes it'll work for one argument but not the other. But the problem is that if we plug it in here, if it were negative, then we can't calculate this. So the whole thing becomes irrelevant. Okay. Okay, let's take another example. Like I said, we're just going to do a whole bunch of these. These are all very, very similar problems. So we have log base 2 of x plus log base 2 of x minus 2 is equal to 3. Okay. So here we only have 2 logs on one side, so we only have to condense one side. So if we condense one side, we get log base 2. We're adding, so when we condense, we multiply. Again, you can skip this step and go straight to the next one. I'm doing this step just for everybody who's watching, it's just so that you can follow along and see what's happening. Okay, so you want to condense the logs. As soon as you see more than one on a side, you're going to condense. Okay. And this is what I mean. You could skip right to here where you're multiplying. Okay. Now you have two options. You don't have a log on the other side. So because you don't have a log on the other side, you can't set arguments equal to each other. This is not an argument, okay? So we can't say x squared minus 3x is equal to 3. 3 is not an argument. So either you have to create an argument, or you can put this in exponential form. So we're gonna do both, okay? So everything from here on out, I'm gonna put in red, and then we're gonna do it again using a different method, okay? So we'll call this method 1. Again, it's whatever you're most comfortable with. I don't really care. Okay, this is method 1. So your next step would be to put in exponential form. The idea is that the right side doesn't have an argument. There is no log. Can't have an argument if there's no log. So when we put this in exponential form, what you get is 2 to the third is equal to x squared minus 3x. And then what we have here is we have 8 is equal to x squared minus 3x. Subtract 8 from both sides. You get x squared minus 3x minus 8 equals 0. Okay? So you're putting it in an exponential form, and that's where you get 2 to the third equals x squared minus 3x. And you get 8 equals x squared minus 3x. This is quadratic, set it equal to 0. Now before we go ahead and we do any more, we're going to do the second method, okay? The second step is just a little bit different if we do the second method. And then we can go through and we can solve the quadratic, okay? So on the next page, I'm going to rewrite this log base 2 of x squared minus 3x. And this time we're going to use the second method. Okay. And the second method is to multiply by log base 2 of 2. We're going to multiply the right side by log base 2 of 2. Now the reason why we're multiplying by log base 2 of 2 is because log base 2 of 2 is 1. Okay, that's the first thing. So we're multiplying by 1, so we're not changing the value of the equation, okay? 3 times 1 is 3. Nothing is changing about the values. And we're using base 2 . because that's the base that we have on the other side. So what that gives us is log base 2 of x squared minus 3x is equal to 3 log base 2 of 2, which is the same thing as 3. We haven't changed anything. Now we can move this into an exponent. So we have log base 2 of x squared minus 3x is equal to log base 2 of 2 cubed. So now we have the same base, so we can set the arguments equal to each other. So now x squared minus 3x is equal to 2 cubed, or x squared minus 3x is equal to 8. Okay, subtract 8 from both sides and we get x squared. This is where it goes back to where we were on the other side. Minus 3x minus 8 is equal to 0. Okay, and that's where we left off. So the second step, notice this is more steps than the other method. The other method is just going to exponential form and you automatically get that 2 cubes equals x squared minus 3x. In this method, it takes a couple more steps, right? We have to multiply by log base 2 of 2, then get the exponent into, then get the coefficient into the exponent, and then we can set the arguments equal to each other. So it's another, it's like 1 or 2 extra steps, depending on if you skipped a step, but ultimately you get the same thing. Okay, now we're gonna solve the quadratic. So we can go back, and now our step 3 is to solve our quadratic. And that's the same for both methods. So we could use whatever method we want. Most of the time, I'll be honest, you're going to get something factorable. Okay. Except for here. Is this factorable? Oh, I made a mistake all the way through this. I'm so sorry. I'm gonna just erase it. I made a mistake. I put x minus 2, right? This should be an x minus 2 over here. So I'm just gonna erase everywhere I wrote a 3. I'm gonna erase it and write a 2. I'm sorry, that was totally my fault. We'll just rewrite. So this is x times x minus 2. I got confused with the extra 3 in there. This becomes x squared minus 2x. The 2 to the third doesn't change. It's just everywhere where we had an x squared minus 3x, it's really an x squared minus 2x. You might have caught this before, so hopefully now that you have watched this part, it's not too confusing. Some of you may have caught that mistake earlier. I caught it here because I realized that it should have been factorable. So again, we're just replacing all of these 3's with 2's, and then it's factorable, so it makes it much easier. So everywhere where you saw a 3x, it's really a 2x. I'm sorry about that. So now this is factorable. X squared minus 2x equals 8. It was supposed to be factorable. Most of the ones that I'm going to give you will be factorable. So we need two numbers that multiply to -8 and that add to -2. The two numbers would be -4 and +2. Which means that our factors are x minus 4, x plus 2 equals 0. We use the 0 property. So x minus 4 equals 0, x plus 2 equals 0, x equals 4, x equals -2, and here for the first time you're going to see extraneous solutions. So if you remember, I told you plug it into the original equation, okay? So our original equation, these are your arguments. So you can automatically see that x equals -2 is going to be extraneous, because when we plug this in, we shouldn't get a negative argument. That is not always the case. It's not always that if the x is negative, it's not going to work. So you really do have to plug it in. As soon as it doesn't work for one of the arguments, you don't have to plug it in for any of the others, okay? If we plug in x equals 4, that does work. This makes this argument positive. Then we have to keep going. So we have to make sure it works for every argument. 4 minus 2 is also positive. So the x equals 4 is okay. The x equals -2 is extraneous. So let's just go and write that in the notes here. So 4 is greater than 0. And 4 minus 2 is greater than 0. But -2 is not greater than 0. Okay, so this is extraneous. This one is not. This one is fine. Okay, let's take another one. At this point, you might at each one sort of pause, do it yourself, and then you can go through and see if you understand how to do it. At this point, we're just going to go through, I think I have like 5 or 6 more. So pause it after each one and just see if you could figure out how to do it. Okay, so this is number 5. And they're all going to be a little bit different so that you get a little bit of experience with each type of equation. So this one we have log of x minus 2 plus log of x minus 3 is equal to the log of x squared minus x. So this one is already it's already condensed on the right side, but we have 2 logs on the left, so we have to condense that. So, and the bases are the same. Remember, you always want to check to make sure that the bases are the same. So we're going to condense on the left. So on the left, we're multiplying x minus 2 times x minus 3. If you want to skip this step, that's okay. X minus 2 times x minus 3. Everything in the first set of parentheses gets distributed to everything in the second. So we get x squared minus 5x plus 6. And then we have log of x squared minus x on the other side. So notice in all of these, at a certain point, we get that the bases are the same, so we could set the arguments to be the same. We have log on both sides, so that's what we're doing. In the previous one, we had a log only on one side and just a number on the other. So in that case, we can do one of two things. We can put it in exponential form, or we could use that second method. Here, we don't have to worry about that. So here, we could set the arguments equal to each other. Now this appears to be quadratic, so we're going to solve this like a quadratic equation. We're going to set it equal to 0 by subtracting. We can subtract it, it doesn't matter how you do it. I'm just going to take this and move it over to the left side. Okay, so I'm going to subtract x squared from both sides, and then add x to both sides. That'll cancel out everything on the right. And what's kind of nice in this problem is that the x squared cancels, so we actually don't have a quadratic. And if you saw that, you might not do both things at once. Okay, so in other words, you might not add x to both sides to cancel it out. Again, that's up to you. I just did it both at once, but you don't have to. So what we get here, and be careful, is you get negative 4x plus 6 is equal to 0. Now we have this equal to 0. We need the numbers on one side and the coefficients on the variables on the other. So we're going to add 4x to both sides here. If you hadn't added this x here to both sides, then you would have had a negative 5x plus 6 equals negative x, and you would have been adding 5x to both sides. That would have been the difference. So here, we add 4x to both sides. We get that 6 is equal to 4x. Then you're going to divide both sides by 6. And you get that x is equal to 2/3. So again, you have to go through and you have to check these. And it turns out that if we plug in 2/3, this is extraneous. So 2/3 minus 2, you don't even have to use fractions, okay? You can just think about it. 2/3 minus 2 is less than 0. This is a number that's less than 2. So when we subtract 2 from it, we're going to get a negative number. Okay, so we don't have to even really think about it. And as soon as we realize that this is less than 0, we're done. We don't have to do any of the others, because once one argument is negative, that's it. So this is extraneous. Okay, so that's it for that one. Okay, let's take, I'm sorry, I did this wrong. It's been a long day, I guess. We're dividing both sides by 4 here, so we actually get something totally different. It actually turns out to still be extraneous, so it does matter, but we're dividing both sides by 4. So what we get as our answer is actually 3/2. But 3/2 is still less than 2, so it doesn't matter. That's still an extraneous solution. Sorry about that. 3/2 is still 3/2 minus 2 is still, this is a number that's less than 2. This is just 1.5. So we still get something extraneous. Okay, let's do another example. Okay, so again, We're just doing a bunch of different examples. Do them on your own first. And it's just going to be a mix and match of a lot of different things. Okay? Things that, some of which you've seen, but everything that you would know how to do on your own at this point. So let's take the log of 4x minus 15 is equal to the log of 6x plus 9. Okay, so here we have one log on each side, so we don't have to worry about condensing. The base is the same, so the arguments are the same. So we're back to that nice little linear equation that we have. 4x minus 15 is equal to 6x plus 9. And we have a nice little linear equation. This is a nice fast one to solve because we can subtract 4x from both sides, subtract 9 from both sides. That gets the x's on the right and then constants on the left. There's no, the only reason it's sort of coincidence that the x's always wind up on the right. The way I do it is I try and make my x's positive. Okay, so how you do it is up to you. So negative 15 minus 9 is negative 24 is equal to 2x. These canceled. These canceled. We divide both sides by 2. And we get that x is equal to negative 12. This is extraneous. We only need to put it into one of them, but it is extraneous. 4 times negative 12 minus 15 is less than 0. So this is an extraneous solution. What it means is there is no solution here. Okay? There is no number that when you plug in, you're going to get something that works. There is no way that the left side is going to equal the right side. That's what this is telling us. Okay. Let's try the next one. So we have the ln of x minus 4 plus the ln of x plus 2 is equal to the ln of x plus 10. I wrote x plus 2. I didn't mean to write x plus 2. I meant to write x plus 10. Okay, so this is a case where we have 2 logs on one side. Remember, ln is a log. And one on the other. So we have to condense. Okay, this requires condensing. So we have an addition sign. So to condense, we multiply. So we have the ln of x minus 4 times x plus 2 is equal to the ln of x plus 10. Okay, when you have 2 logs on one side, it requires that extra condensing step. So now we can multiply x minus 4 times x plus 2. That gives us x squared minus 2x minus 8 is equal to the ln of x plus 10. Bases are the same. These are both ln, both base e. So the arguments are the same. Okay. Now this appears to be quadratic. There's no x squared on the other side. If there's an x squared on the other side and it's the opposite sign, we know that they're going to cancel. But you can always just go about solving it, set it equal to 0. So we subtract x and subtract 10 from both sides so that it's equal to 0. This gives us x squared minus 3x minus 18 is equal to 0. And remember I said These are going to be pretty much all factorable. You don't have to solve them by factoring it, though. You can always solve it using quadratic formula or completing square. So we have two numbers that have to add to -3, but multiply to -18. So we're looking for factors of 18. And those factors are 6 and 3. So it's going to be a -6 and a +3. Okay. So our factors are x minus 6, x plus 3 is equal to 0. So x minus 6 equals 0, meaning x equals 6. And x plus 3 equals 0, meaning x equals -3. We need to check for extraneous solutions. So we have to plug in. Here we have to plug in 6 to all of them. 6 minus 4 is greater than 0. 6 plus 2 is greater than 0. 6 plus 10 is greater than 0. So 6 is a solution. Now we're going to check the -3. -3 minus 4 is less than 0. So this is extraneous. Okay, so that's it for this one. So it turns out that our x is negative here, and it happens to create an extraneous solution. But again, that's not always going to happen, okay? This is just by coincidence. So you should always check both solutions. The -3, we only had to plug into the first argument, because as soon as it's outside the domain here, you don't have to bother with the rest of them, okay? Okay, let's take another one. This one is a little bit different. And again, I would try pausing the tape, because even though this one is different, you're still capable of doing it. So we have ln of x plus 4 minus ln of x minus 2 equals ln of x. Now here's why this one is different. This one is different because we have a minus sign instead of a plus sign. And all of the other ones we've condensed by multiplying. But we have a minus, so instead we have to condense by dividing. So this is going to become ln of x plus 4 divided by x minus 2 equals ln of x. Now this is okay that this happens, okay? The arguments are the same, so we set the arguments equal to each other. Okay, so what we use here instead is we use the quotient rule. And the quotient rule says log base b of x minus log base b of y is log base b of x over y. We use the quotient rule for this. Okay, that was the difference. So now we can solve. So what we're going to do is we're going to multiply both sides by x minus 2. That's going to get rid of the x minus 2 in the denominator here. Okay, so the x minus 2 cancels on this side, but we have to multiply it on the right, and we distribute. And I want you to notice that if your x winds up being 2, it's not going to work, but that's okay. It's not going to work here either, because we'll get a ln of 0. We need it to be positive. But it's not going to work over here, because 2 minus 2 is 0, and we can't be dividing by a 0. Okay, sorry, I wanted to make sure it was recording again. The little record sign goes off my screen, so I'm never sure. Okay. Okay, so what we wind up with is, we'll move this to the next page, x plus 4 is equal to x times x minus 2. And we distribute, so x plus 4 is equal to x squared minus 2x. So this is quadratic, so we set it equal to 0. So we subtract x and subtract 4 from both sides. So this goes away, and we wind up with x squared minus 3x minus 4 is equal to 0. Okay. It's quadratic, it's factorable. You need two numbers that multiply to -4, multiply to our c, and add to our b. That's going to be -4 and +1. Okay, which means that this becomes, I'm going to move this up here just so that hopefully we have room on this page for the remaining problems. So this becomes x minus 4 times x plus 1 is equal to 0. So either x equals 4 by setting x minus 4 equal to 0, or x equals -1. And we have to plug this in. We have to make sure that they're not extraneous. So the original problems, if we go back to this, this was the original, so we have to plug in 4. 4 plus 4 is greater than 0. 4 minus 2 is greater than 0. 4 is greater than 0. So that all works. The -1 plus 4 is negative. Okay, and we could stop there. We could even just plug it in here. -1 is negative. Okay, so let's just show that we plugged it in. You have to show that you plugged it in so that I know I can't read your mind. So 4 plus 4 is greater than 0. 4 minus 2 is greater than 0. 4 is greater than 0, so x equals 4 is a solution. And -1 minus 2 is less than 0. So this is extraneous. So you only have to show that it doesn't work for one argument, but you have to show it does work for every argument. So that's extraneous. Okay, I've got 2 more for you. So let's do the remaining 2, and then that's it. This gives you lots and lots and lots of practice. Okay. So let's do number 9. This is similar to the last one. Log base 4 of x minus log base 4 of x minus 1. And this is equal to 1/2. Okay. So we have 2 logs on the left, so we have to condense it. So we get log base 4, and we're dividing. X over x minus 1 equals 1/2. Okay. And this is an example where you're either going to set it equal to, you're either going to convert it to exponential because we have a number on one side and a log on the other, or you're going to multiply both sides by log base 4 of 4. So let's do both, okay? I'll do one on this side over here, and then I'll do the other on this side over here, and when they wind up the same, we'll just sort of meet in the middle, okay? So if we convert this to exponential form, we wind up with 4 to the 1/2 is equal to x over x minus 1. And 4 to the 1/2 is 2, right? 4 to the 1/2 is equal to square root of 4. So we get 2 equals x over x minus 1. Okay, so to be clear, what we did here is we converted to exponential form. And then this 2 came from the fact that 4 to the 1/2 is the same thing as the square root of 4. Okay, now this wasn't the only option. The other option was to multiply by log base 4 of 4. So I'll just put a little line over here so that you see the difference. This is a different method. That wind up really crooked. It doesn't look as crooked on my paper. That's a little bit better. So what we're doing here is we're doing log base 4 of x over x minus 1 is equal to 1/2, but this time we're going to multiply the right by log base 4 of 4. And the reason that we're doing that is so that we wind up with an argument. Log base 4 of 4 is 1, okay, so that is fine. We're not changing the value. 1/2 times 1 is just 1/2. So then we have log base 4 of x over x minus 1 is equal to log base 4 of 4 to the 1/2. Okay. And then we can set the arguments equal to each other. X over x minus 1 is equal to the 4 to the 1/2, which is just 2. So this is where we meet up. X over x minus 1 equals 2. Okay? So I'll write that down here. And we could essentially do what we did before. We're going to multiply both sides by x minus 1. The x minus 1 is going to cancel here. We distribute the 2. And we get x equals 2x minus 2. So now we can subtract x from both sides. Sorry, subtract 2x from both sides. And I am going to bring this up here so that hopefully we have room for the last problem on this page. And what that gives us...
Hey, yeah. I opened a SoFi Money account.
So we wind up with negative x is equal to negative 2. We divide both sides just by negative 1. So x is equal to 2. Okay, and we're going to plug it in to both arguments. 2 is greater than 0. 2 minus 1 is greater than 0. So this actually is a solution. Okay. Okay, last one. So what we have log base 2 of x plus log base 2 of x plus 2 equals log base 2 of x plus 6. Hopefully you are becoming an expert at these now. Okay. So again, we have 2 logs on one side, so we have to condense. So we get log base 2 of x times x plus 2. Again, you can skip this step. This gives us, we multiply on the left side, we get x squared plus 2x. You can multiply here, or you can multiply after you set the arguments equal to each other, it really doesn't matter. So once we do that, we can set the arguments equal to each other. Notice the steps are the same always. This looks quadratic, so we're going to move everything over so that it's equal to 0. So we subtract x and subtract 6 from the sides. Which gives us x squared plus x minus 6. Okay, and I'm going to move this up here. So what we're looking for is two numbers that add to 1 and multiply to negative 6. So those two numbers are negative 3 and 2. So those are our factors. X minus 3 times x plus 2 is equal to 0. 0 property says x minus 3 equals 0, so x equals 3. X plus 2 equals 0, so x equals negative 2. So we have to make sure that nothing is extraneous, so we're going to plug these in. So the 3 is going to work. Okay, some of these you're going to see right away, but again, you have to plug it in so that I know that you knew how to do it. If you just box it, I don't know that you knew to plug it in. Okay, so 3 plus 2, 3 is greater than 0. 3 plus 2 is greater than 0. And 3 plus 6 is greater than 0. So we're okay here. But here, negative 2 is less than 0, so this is extraneous. So the only answer here is the x equals 3. Okay. So these are just lots and lots of different examples of logarithmic equations. So hopefully from here you'll feel pretty comfortable, and that is it.